speed.
Match rail 1.
Oh, you shall step up. You step it up tonight. Hello, Matt.
Hello, Stuart.
Thank you. Okay.
I told it all to you upstairs.
I know, yeah, but we're not starting with that. How did you get involved in science?
How did I get involved in science? So, my dad was a scientist, and so I guess the apple doesn't fall very far from the tree. But I was always, I was inspired by my father. And I was always curious about the natural world. I was really keen to understand how it works at a more fundamental level. And there's such a joy in learning about the natural world, and that's always inspired me.
So you went to high school. And what did you do in high school? So you made the leap from high school to university straight into science, or did you do something else?
It was a bit of a complex story. We were oh, okay. We were refugees from communist Poland, so we bounced around a few countries. And eventually bounced from Italy, of all places, to the US and bounced into Australia. And I started my high school here.
Wow, was not expecting that. So how old were you when you got to Australia?
11.
First thoughts?
Arriving in Australia. First thoughts, actually, I remember all these blokes at the airport with the shorts and the long socks, and I thought it was the most ridiculous thing I'd ever seen. Okay, they had ties, and second thought was we arrived pretty close to Christmas, and I remember spending Christmas at Manly Beach, just on the beach, and I'm just thinking, this is epic. What a way to! I thought this is, and the third place was we lived in Drummoyne. The university put us up. My dad worked for the university on the coast, and I remember my brother and I sitting around thinking, "Gee, what a heck little town, you know." But look at what it's grown into now. So,
What, Sydney? Or...
Sydney. Yeah. We came from the United States. So
Whereabouts in the States? Well, your father obviously got out of Poland because he was a scientist. He managed to migrate to the United States from university? Or?
No, we escaped from Poland. We got out. It's too long a story to tell, and I'm sure you wouldn't be interested. But we got out after the Prague Spring uprising in Czechoslovakia, and that was in 1968. And in '69, there was a tremendous amount of anti-Semitic activity, and that the government opened the borders. And my mother wasn't Jewish and decided now was the time for us to, and it's too long a story to tell, but we managed to escape through the Iron Curtain, and that I'm forever grateful to my parents for it was such a courageous leap into the unknown.
And from there to the States and again science?
A little bit of bouncing around. We Austria, Italy, then the US.
No, you just caught me flat-footed in that one. I wasn't
I'm
expecting.
sorry, Stuart.
No, that's good.
Yeah.
That's interesting. I found it interesting. So your dad was a scientist and
Yes.
seconded to Sydney, you live? Or...
So my dad struggled a bit when we fled from Poland. My dad had 2 academic positions there, but his qualifications were never really recognised in the West. He really struggled. So he landed, again, we bounced around a lot. He landed a very junior academic position at Portland State University in the United States. And then when that finished, he landed a very junior academic position at Sydney University, and that's why we came to Australia.
Okay, so you finished high school. Which high school?
Marsden High School in Sydney.
North Shores?
No way, no. A slightly less bougie area in Ryde, West Ryde, yeah.
Timlin's from Ryan.
Well, now it's bougie.
Despite my input, yes.
It was the drug dealer index was a little higher when I was a kid. I'm sure that's changed. Please edit that out. Okay, that's. Yeah.
They're going to run up past you, you say.
Like
Thank
live
you.
to air, like I said.
What's that?
Like I said, live to air.
Oh, thank you. Yeah.
So you finished university Marsden High. So you went to uni. But you must have. Did you go straight to science? Was it
Yeah.
what you wanted to do?
Yeah, a little bit. Yeah, I mean, we're so grateful as immigrants to Australia. I was lucky to enter Sydney University. I got a free education. I mean, I think had we had stayed in the, for my career, I was lucky enough later to go to Princeton University in the United States. If we had stayed in the US, I think there's no way we could ever have afforded for me to have that opportunity. But because I was lucky enough to get an education here in Australia for free, starting at Sydney and then later at Melbourne University, it gave me such a catapult. I'm so grateful for that.
And what subjects did you read?
Did I read? No, there was at the bar a fair bit. But I always loved chemistry, physics, and mathematics. Is that they really? It's funny, I just can't understand. People talk a lot about STEM subjects not being fashionable. For me, they're just the hottest thing ever. These were the tools to understand the universe in a deep way, and that gave me such a joy. I couldn't get enough, and I was lucky enough to be inspired by a good science teacher at Marsden, and also at Sydney University, so some good chemistry teachers.
So then you did a doctorate, I guess.
Yeah, I worked in industry. I got quite frustrated with universities in second year. The Ivory Tower Index was back then it was a very aloof place, not as connected to the real world as I would have liked. So I worked in industry between second and third year. There was a program, and then took a job after I finished honours year to work in industry again. I worked for a company called ICI in Melbourne, and then went back after that. I got frustrated in industry. My career is one of frustration. Went back to finish a PhD at the university, or to start a PhD at the University of Melbourne.
Yeah, what was your PhD on? What did you pick?
Yeah, it was a mixture of chemistry, physics, and mathematics, and I loved it. It was a multidisciplinary approach to try to develop a technology to see soft molecules like proteins on surfaces, and prior to that, you can only image such things with a giant synchrotron, and we developed a system that could do it for a small amount of money, $10,000, $20,000, and I loved developing that, and I loved the new discoveries that came from this. It was challenging, but it was a lot of fun.
So you got your PhD.
Yep.
And you went into research.
Well, PhDs, I would argue, are about research, but I decided to continue in research. I was lucky enough to win a Fulbright fellowship to go to Princeton, and so I started my postdoctoral career there. There was a new institute there which really influenced me. It was, again, a multidisciplinary institute with this idea of tackling really, really hard problems by getting input from physics, biology, chemistry, mathematics, engineering. I loved that idea. I just enjoyed my time there.
That's unusual, isn't it? It's like spreading the information from different areas of science.
It's interesting. It shouldn't be unusual, but even today, I think it remains a bit unusual. Certainly back then, and still I think today, we tend to be more monodisciplinary. We like to as humans, we like to flock together in our own little tribes. There are good things about that, but I think we need to get out of those tribes more. And certainly back then, it was quite radical to mix up people with a chemistry background and people with a biology background, physics and engineering. And again, I was inspired. I loved it. I just thought there's so much to learn, right? I'd learned about chemistry and physics and some maths, but here I could learn about biology. It was amazing.
Was there a culture shock going to Princeton after Sydney?
It was a culture shock going to Princeton, yes, after Australia. It's a far more competitive place. I think the way to think about it, at least my perspective, is, it's a bit like if you play for a really good baseball team or a really good basketball team here in Australia, and then you go and play in the Pro League in the US. It's a bit of a jump. All of a sudden, the whole world is there, and the temperature is up. And I should have been a bit more prepared for that. But in the end, once you get the swing of it, it's exhilarating.
Well, they gave you everything you wanted and expected you to perform, wasn't it?
More the latter. I think it's the environment I experienced really was a sink or swim. It's a competitive. Unfortunately, science globally these days can be a bit competitive. At some of those places, it's quite competitive, and it's, you're here. What have you got? Show us. So there's an old golfing quote, I think, if you haven't, it's about someone, I think, who was competing on in some tournament. If you haven't brought it with you, you're not going to find it here.
I can identify with that in golf. How many years in Princeton then?
I spent 4 years in Princeton.
That's in Massachusetts, right?
No, it's in New Jersey. It's about 1 hour out of New York.
So then straight back to Australia.
Yeah, that was a really difficult decision. Gee, this is all personal, right? That was a really difficult decision for me. I had a faculty position that was coming together there in the United States, and it was such a difficult decision to either choose. I knew that if I stayed then in the United States, I probably would never return to Australia. But I love this place. It's just the lifestyle. This is the place I wanted to raise my family. I'm so grateful that I've raised my family here. It was one of the most difficult decisions of my life, and I chose, there was a position that became available at UQ. I applied for it, was lucky enough to get it, and made the decision to move back. I don't regret it.
So you came to Queensland. Then what was your position?
So I came here as a lecturer in chemistry. And it was an interesting time here. Back then, the University of Queensland was not as research active as it is today. I think today, UQ is a powerhouse in research. It's a powerhouse globally. It wasn't really as much back then. And I think I was lucky that I came back at a time before the Chuck Feeney era, which Chuck Feeney is a major philanthropist who donated hundreds of millions of dollars towards medical research in Australia. He donated $20 million towards this institute, the Australian Institute for Bioengineering and Nanotechnology. And that really was such an exciting time to be part of that, where the university got catapulted. It developed not just the ARBN, but 7 institutes. The number of research staff here at that time doubled. We picked up so many people from around the world. It was a wonderful time, golden era, to watch the university transition into a powerhouse research, a global research powerhouse.
Okay, now you're going to have to nurse me through this one. How do you get from lecturing in chemistry to biochemistry, and what do you do here? What is this institute set up for?
Yeah.
My voice won't be on, so you're going to tell me.
Yeah. Well, it's the ARBN's an interesting concept. Originally when we were pitching the ideas, wanted to emulate that multidisciplinary institute that I mentioned in Princeton, where the idea is to use multiple disciplines to tackle hard problems. Cancer is a really, really hard problem. So you need innovative thinking from numerous disciplines. So the idea was to create an institute that would do that and would fuse two emerging areas. One is bioengineering, and the other is nanotechnology and nanoscience. And so where my lab is now, my lab's located in the AIBN, that's the sort of work that we do. We work on trying to develop new technologies that give new eyes on biological systems, the molecular machinery of biological systems. And the molecular machinery of biological systems goes wrong in cancer in ways we don't yet quite understand. So we need new tools, new ideas, radical new ideas or radical new technologies to try to get eyes on where has that machinery gone wrong and how can we fix it. And so that's something that inspired me very early on. I was lucky enough to have a few mentors. Professor Pam Silver at Harvard, where I spent some time in her lab, was a tremendous mentor in this space. And it was also a place where I could use my background knowledge in chemistry, physics, mathematics, to try to create something new for biology and medicine and for cancer patients.
Well, you say cancer, but you studied biomedical, or whatever you. You made a conscious decision to research cancer, right?
Yes.
When and why?
Yeah, I guess I think, as with so many of these things, it's personal. A number of my friends, dear friends, died of the disease, and I don't recommend this to anyone. But it is the most agonising thing to watch this disease. And I learned how evil this enemy is. It's a terrible enemy. And the other part that I learned was I was lucky enough to be involved in one of the pivotal technologies about 20 years ago is a technology called DNA sequencing. And my lab got drawn into that space to start developing aspects of that technology. And it was an eye-opener that DNA sequencing now has changed the way that we understand cancer and is changing the way that we treat cancer. And that just galvanized me that, someone, I wasn't trained in biology, someone trained in chemistry and physics, maths, could be involved in that sort of journey. For me, was like jumping on the ship with Columbus. It was, really, really.
I'll let you expand on that if you want. The voyage. Are you science fiction reader? Do you like Star Trek?
Sure. Yeah, sure. Who doesn't?
You boldly going where no person's gone before.
Yeah, but isn't that what research is all about? It's not about anything that's known. It's about what's not known. Yes, I don't mean to sound like Star Trek, but boldly going somewhere where no one has gone. And, I remember when I was a student, there was a Swedish professor that came and talked to us, and he said, why do young people go into science? Pay's not so great. It's actually not too bad, I don't think. The hard part is getting the job. Not enough jobs, problems. Why do young people go into science? And he gave an answer which really resonated with me. He said, well, they're the people who would have joined Columbus. They're just not satisfied with a world where everything's known. They have to be at the frontier where we don't know the answers. And you're involved in unraveling those mysteries. That's a rush. That's for me, that's the crack cocaine.
I'm a little bit nervous. Did we just cut
Just
for a
going
second?
up and down.
Yeah, we just cut for a second, Steve.
Huh?
Atmos Interior,
Atmos.
Matt Trow interview. Just 1 minute.
It's very personal. You should. Oh.
Sorry, start again. 1 minute.
See, Andrew, you don't explain what Atmos is and expect them all to do
I'm
it.
so sorry.
I'll explain
Okay,
later.
here we go again.
1 minute of silence.
Quiet, please. And go.
Atmos is short for atmosphere. So when you shoot in different... That was your first Columbus moment.
And rolling in.
If you had one. I mean,
Yeah.
You've gone from, okay, lecturing in chemistry. Okay, you've started new biochemistry.
Well,
Laboratory or
started a
being
lab.
part of it.
Yep.
Was it your lab or somebody else's lab?
No, it was my lab.
From
Yep.
the get-go.
I was lucky enough to, the original appointment at UQ gave me the opportunity to establish my own lab. I was very grateful for that.
Now what do you do now? You go try that. What are you going to do with it?
Cool stuff. Go to the unknown.
Well, the unknown's going to present itself, so...
Well, it's got to present itself, but also you've got to poke and prod and find it, right? Because everybody's, all the easy stuff's been done. And so a lot of the time, there's a quote from Stephen Hawking, right? He spent, I think, a huge part of his first year of his PhD finding the question. The question, I think the quote, and I've got to do the quote justice, I probably won't. The question can be more important than the work. You may not succeed in answering the question, but finding a really good unknown is a treasure. So it doesn't always present itself, but certainly in cancer, it's replete with opportunities. There are so many opportunities. But I think your question was there a Columbus moment? I think if for all of us who do research, it should all be a Columbus moment. Every day we should be embroiled in the unknown, constantly agitating to get new knowledge. So every day is a Columbus moment. Some days are better than others. There's a lot of failure. That's how science works. But some days you do get to see that landmass.
Is it failure?
Is it?
You said there's a lot of failure. Is it
Yes.
failure?
Well, that's a good question. Experiments fail. However, it's only failure if you don't learn from them. It's never really a failure because if the experiments are properly designed, you should always be learning from them, and so then eventually you're able to make a new discovery. A new discovery for us, I think, the biggest moment was I mentioned that we were playing around with these DNA sequencing technology as technologists. We got involved in some clinical trials, and all of a sudden could see things in cancer that no one had ever seen. And then all of a sudden, we could see the impact of some of that work in the survivalship and of certain patients. That was a pretty big moment.
What was it?
Okay, so we were developing a technology. This is going back quite a while. It's going back almost 10, 15 years.
It's yesterday.
Yeah, so we're playing around with DNA sequencing was new. With humans have really we've only known about DNA or the structure of DNA since Watson and Crick. Only how many decades was that? Probably 4 or 5 decades ago. We've only started reading the code for a few decades, and it's only been the last 15, 20 years that we've been getting the information and trying to discern the code. So for us, we were trying to, we were involved in a clinical trial where trying to show that we could sequence a patient and get usable information in under 7 days rather than 6 months or 12 months, because they'll be dead by then. We're involved in a clinical trial, and it did influence the trajectory of one patient. The doctors that were treating that patient chose to treat her with a melanoma medication, even though she had blood cancer. And it knocked the cancer down. And it was a fall off your chair moment. It was, here I'm playing around with gadgets, and this has had an impact on I don't need more than that.
Do you want to tell me that anecdote again? Only because we had an air conditioning change.
Oh, right. Well, just maybe get me into feed me the...
Oh, no,
so-
there's the anecdote. This is a great moment. You've actually found what you're doing has proved
Useful in the
made a
clinic.
difference.
Yeah, it's made a difference.
And you found a patient. I'm sure you've told that anecdote a million
It's-
times. It's exciting.
It's.
Go on.
I gave a TEDx talk on it.
Yeah, okay.
So
I've seen it.
it's patient 205. Yeah, Alex. Yeah, that fundamentally transformed my thinking.
Just take it from the beginning and tell me the 205 story, if you don't mind.
Yeah, so we were playing around with a new type of DNA sequencing technology for cancer. And our goal as technologists was to show that we could sequence a patient, get useful information in under 7 days rather than about 6 or 12 months, which is what it would usually take. 6 to 12 months, the patient will be dead. So we're involved in a clinical trial, and the goal from our side, because we don't see patients, was to prove the technology, show that it could be done, schmick it. But the information did influence some of the clinicians. We didn't realise, but we learned after the event that they changed the medication of a blood cancer patient, Alex, patient 205. She had blood cancer, and they used a melanoma-style medication, and it made a difference. It reversed her cancer. And that it's a fall-off-the-chair moment. It was a fall-off-the-chair moment for me. I just couldn't, but my God, it's something some trinket we're playing around with in the lab could have that impact for someone's life. I don't need more than that.
That's enough to hold. That's what I meant. Mr. Timmons knows.
More than hook.
Have you a question?
More than hook.
More than-
I think you could probably imagine.
So that changed your future from that point on?
I think it really accelerated the passion to move into this space. I really learned that that getting new eyes on cancer through new technologies could have a transformative effect, not only on our understanding of cancer, but eventually, once it's translated appropriately, on the care for patients.
Where's that led you now?
Do you want me to talk about our current research?
Would you like to talk about your current research?
If you would, if it would please you, of course. Sure.
You gotta make it fun for the audience. Where'd you start and how'd you get here? Because it's pretty bloody exciting, man.
Well, it's very personal. I hope it's not dull, right? So,
I haven't found it dull so far, Steve.
No.
Okay.
Sorry, Matt, I just get you to lean back the mic. Yeah, that's it, thanks.
Okay, current research. Yeah, so again, my background is in chemistry, physics, and mathematics, and our lab has a sort of an unusual approach to cancer research. We try to not only pick really hard problems, but we try to develop entirely new technologies to, as I mentioned, get new eyes on cancer in ways that no one could, we're just not able to at the moment, to either help understand the mechanism of cancer better or to help patients in the future. So currently we have 2 programs, and it's kind of like the tale of 2 chips, right? The first program is what I'll call a single molecule readout chip. And can I show you a prop?
Sure.
This is one of the chips. There's a little opalescent dot on this silicon wafer which has millions of little nanopillars. Each nanopillar reads either a molecule or what's called an extracellular vesicle. It reads either a text message or an email.
I
That,
just hold you there for a
yeah.
second. Sorry, Matt.
Sorry, Matt.
Yeah, just go for a second. So I just want to. I think it might be good if we shoot the props standalone.
No batteries required.
it's a crack, right?
Three.
Fuck that.
Well,
Isn't there an AI version of this? You know,
costs thousands of dollars.
There was. It's not
it's no good. This works. Okay.
It's the coolest thing you've been involved with. Use that. Go for it.
Look, it is. I feel so lucky. The current research that we're doing, I think, is some of the most. It's the most exciting research I've ever been involved in my life, and I'm so lucky to work with, I think, the best people. That science these days is totally a team sport. I feel so lucky to work with the team of people that I'm currently working with. It's sensational.
What is it?
So there's two key areas of research we have going in our lab at the moment. The first one, it's a tale of two chips, if you like. The first one is what I call a single molecule reader. This is it. It's a little piece of silicon. It's a silicon wafer. On there, if you look closely, there's a little opalescent dot. That dot contains millions of little nanopillars, little nano hairs. Each little hair, if I were to take a drop of blood, can detect single molecules or single extracellular vesicles. I'll explain what I mean by that. They are, the best way to describe it, they're like the text messages or emails that cancer cells send to each other. It's a bit of a team sport in the body as well. The cancer cells are always communicating with each other. They're also communicating with the immune system, trying to outflank the immune system. So they send these little messages, and they're present in the blood at trace. And we try to hack into that messaging system on the chip. It's really, really exciting work because it can give us insights, for example, during cancer therapy, whether things like immunotherapy is working or whether it's doing damage to the body. These are critical issues in the trajectory of a cancer patient, and having these sort of eyes on whether the drugs are working, whether they're causing damage to the patients, is absolutely critical for converting cancer from a deadly disease to a managed chronic disease.
How does it do that?
So what it does is, as I mentioned, the cancer cells are sending messages all the time. So to understand how to treat those cancer cells, or the cancer, we need to hack into those messages so we can learn what circuits have gone wrong in the cancer. The way it does it is floating around through the body are molecules. They're called cytokines, and they're also little nanoparticles called extracellular vesicles. They're at such trace level concentration that you need a special technology that's incredibly sensitive to be able to pick them up. And that's what this does. And we're able to catch. It's a bit like going into the internet and trying to catch those emails and texts only from the terrorists and not from everybody else. That's what the chip does. And once we catch those emails and texts, we learn so much about that person's cancer, and that can guide their treatment in real time. Does that make sense?
It makes sense to me. Steve's the silly one. That makes sense to you?
Huh?
What?
Absolutely. Crystal clear.
Do you want me to talk about the second chip?
Well, you've got to go somewhere with that. It's a bit like, I don't know, Enigma and Colossus, is it?
I don't know that. What Enigma and
Enigma was the German code in World War II, and Colossus was the machine that Alan Turing built and eventually planned to crack it.
It's exactly that. We got to crack. It's about cracking the communication system that cancer is using. So that our hypothesis is that the vast majority of cancers that occur in our body are eliminated by the immune system. A small subset, very, very tiny subset, fools the immune system. And that there are a number of ways that it does it. One of them is this messaging way. And so to hack into that messaging system gives us new eyes on curing the disease. And I use the word curing carefully by, in fact, the more, I think, accurate language would be converting it from a disease that can kill to a disease that can be managed as a chronic disease. And we're seeing that now. That's happening now in the clinic with some of these approaches.
So you are essentially code breaking, is that what you're saying?
We're-
Is that too simple?
It's not a bad analogy. I think it doesn't capture it exactly, but it's not a bad analogy. Where first you've got to receive the messages before you can code break them, right? So we're reading the messages first, and that's a game changer. Then we code break, and then the second chip comes in. So the second chip, this is the reaction chip that looks something like this. We're using our ability to catch these texts and email messages, these are cytokines, extracellular vesicles, to create objects that are exactly like the ones that the cancer is using or the immune system, change the code, and send a correction code back into the body. So to use your analogy of the code breaking, we want to hack it and then change it. And that way change the trajectory of that patient.
To use the full thing, that would be like with Enigma and Colossus, that would be like finding where the U-boat fleet was and then telling him to change course.
100%. Perfect. So I think that's an excellent. So finding where the U-boat fleet is and the immune system, let's say the Air Force that they could stop those, are way off over here. They've been fooled, right? Once we know, you can redeploy the immune system, the Air Force, to where the U-boats are and interfere with their action.
Because that was the greatest problem I actually did have for real a few times with Enigma. They broke it and couldn't do anything because the Germans would know they'd broken the code. So they let Coventry get bombed, or they let transportation fleet get sunk.
But I don't want to overplay the analogy. I don't want to overplay the analogy, but I do like the analogy. I think the problem with cancer is so complex. It's not one disease, it's thousands of different diseases. And it also evolves with time. So it's a war that's not unsimilar to what you've just described. And so to have eyes on which of those thousands of cancers are we dealing is the dominant one? What's the circuitry that's really dominating here? Hack into that and treat that with precision, I think, is a big part of the future. It's called precision medicine.
Have you accurately described the big disc and everything it does?
I've tried to.
Do it again?
What's that?
Do you want to do it again?
Sure. So once we've read the texts and email messages, the cytokine molecules or the extracellular vesicle nanoparticles, on this chip we can assemble exactly those molecules, but this time with our own code, such as an mRNA code or a radiotherapeutic, to create a precision medicine just for that patient. I think that type of precision medicine is the future of cancer therapy.
Where does that lead us?
Where it leads us is, and I think we are seeing this now with cancer, we're kind of picking off cancers one by one. There's thousands of cancers, it's very complicated. We need to know which one's which. Where it leads us is converting cancer from what used to be a death sentence to a manageable disease. It's a bit like what we saw with HIV. HIV, when the outbreak first happened, was death sentence. There was nothing we can do. Now, in the first world, not many people die of HIV. There are medicines that can contain the disease. And I think that's what's going to happen with cancer. We're already seeing that happen in a number of cancers with melanoma, for example, breast cancer. We're just going to see more and more of that. And the arsenal of new therapies, new eyes on the disease that is now converging is sensational. I think we're at a real tipping point in the cancer area. It's an extremely exciting time for not just cancer research, but the translation of this knowledge into the clinic.
I'm lucky to say that again. I'm not sure how much of that television spitting came up. Did you see it, Steve? It changed colours, it flashed and did a lot of stuff to affect the images very quickly.
No.
It's still doing it.
Yeah, but it's not playing on us.
Okay. Just want you to look your best.
Thank you. I
Do you
want
want
to.
to try and compress the excitement of the future as well?
I'm good. Feed me a line. I'm good. I'm very responsive. If
Well, look, you said on the phone it's the most exciting time in history to be part of science and cancer research. And you're going to go, well, why? Where's it leading? And what's so exciting about it? Because lots of other scientists say there is no one hit, there's no one kick, and we know about bespoke medicine, but
yeah.
this is where you're leading us, isn't it?
I think it's so exciting. My perspective is that it's such an exciting time because we're seeing a convergence of a number of things that are entirely unique. The first bit is we have now completely new technologies to give us new eyes on the enemy, new eyes on cancer, to understand the mechanism. At the same time, we've got a number of absolutely brand new therapeutic approaches that are new. Let's talk about immunotherapy, where one is tweaking the immune system, or precision immunotherapy. Let's talk about radiotherapy, precision radiotherapy. We could talk about cancer vaccines. These are nanoparticles with RNA code that are designed to hack into the whole cancer immune system dynamic to tip the scales towards the good guys, towards the immune system. I think with the convergence of those things, we're starting to see cancer converted into, again, a chronic disease rather than a death sentence. And I'll back up those statements with track record in the clinic for a number of cancers, like melanoma. Melanoma, 5-7 years ago, stage 4 melanoma would probably be looked at as a death sentence. Chemotherapy would be the only option. Now, there's multiple lines of alternative therapies, immunotherapies, precision-guided therapies that are extending not everyone's life. It's not as good as we really want it to be, but boy, all those years ago, 100% of people would die. Now, 40% are living beyond 5 years, longer. Some are living 10 years. Some are permanently in remission. I think we're going to see, and we are seeing, more and more of those stories, and we'll see us picking off each of these cancers one at a time.
What about financial? I know, Andrew, that the air conditioning had changed. We don't need to be looking at that.
Yeah.
I think we will on that one, but ACRF, you've
Yep.
never put in for a
We have one. We have a current ACR.
yeah, Tom wants to have dinner with you when he comes to Brisbane in a couple of weeks too.
What's that, sorry?
The general wants to have a drink with you when he comes in a couple of weeks.
They're currently funding us, so without question. Yeah,
tell me more.
without
I have no
question.
idea.
Yeah, of
Because
course.
We're not just doing people for finance for the ACRF, but if you've got anything nice to say, obviously we'd like to hear it.
Of course.
Or even the nature of finance, of funding.
Well, should we talk about that?
Yeah.
It's funny you use the Columbus analogy. I think, to make inroads in science is a team sport. And to make inroads in science and research, you need an ecosystem. You need people. It doesn't work without people. It doesn't work without brains and talent. You need equipment. You need access to patients and doctors. And that ecosystem needs to be sustained. It needs funding. It doesn't work without funding. And so it's a really essential item of progress in this space. It's a bit trite to say that funding's required, but that's why it's required. And the ACRF is an essential component of that. We've been lucky enough to receive ACRF funding in the past. We're very grateful for that. And it's enabled the growth of several researchers in our lab who are now outstanding scientists, and they've made contribution for the ACRF grant in lung cancer. We've developed some of the technologies I've talked about through ACRF funding in lung cancer.
I'm sorry, mate.
No worries.
It's the Australian Cancer Research Foundation.
Australian.
Trying to get rid of many letters.
Oh, of course. Sorry.
Sorry about that. Just occurred to me. I know what you mean. A lot of people like that.
Just prompt me and I'll stop talking. Start talking. I'll stop. Actually, prompt me and I'll stop talking as well.
Well, you started off with the Columbus, and I thought you were about to make the analogy was like, who was the Queen?
Yeah.
Isabella.
Yeah.
Um,
Wouldn't have happened without her, right? Yeah.
well, the very nature is you'd like to think governments do it, but they don't do that. There's a certain amount that governments do, but after that, you're really at the mercy of, well, who are you at the mercy of?
Well, that's a really good question. So our lab's been so lucky to have received funding in the past from philanthropists, and it's so valuable. And I get asked the question a lot, well, why do you need philanthropic funding? Why can't, this is so important, why can't the government do it? You know, the government should just do it. And, you know, the government has all these grant schemes, et cetera, et cetera. The reality is that they do, but in a very competitive, in the real world, where science is competitive, if you look at the statistics, something like 12% of grants will get up. It's very difficult to put forward an outrageously risky proposal and expect that it will get funded. In the standard competitive grant schemes, one needs to show demonstration of proof of concept. It's not required always, but you know, it's one of those nice to have things. And if you're looking at a 12% success score, it matters. And so the really crazy ideas, the ones we should be exploring, miss. So that's where philanthropy comes in. There's a quote I like, I can't remember who said it first. It may have been one of our former vice chancellors. Philanthropy leads. In other words, philanthropy, or organisations like the Australian Cancer Research Foundation, give the engine for those crazy ideas, where you get a little bit of proof of concept, or maybe something's failed and not tried. So when you go to the conventional government grant funding scheme, you've got a better chance for it to be successful. It sounds a little convoluted, but it's extremely important. You know, we need ways to fund those really crazy off-the-wall ideas. Otherwise, we don't progress.
What else do you want to say? What else do you want to say?
Oh, God.
Think about that for a second. Stephen, do you have any questions?
Look, it was interesting to hear you say that cancer sends messages to itself and emails and those things. And I kind of get that, but I'm just wondering, why is it that cancer needs to send messages? And I mean, exactly what is it that does? I mean, you say it's like emails, but is it some sort of electrical impulse like through neurons? Or is it
It's like chemicals that's sending.
Now, if you look at me,
Yep.
answer his question, you look at me.
Right.
Continuity therapy.
Yeah, the cancer cells they're emitting chemicals. Those are the messages. It was one of the primary messages that it sends. A primary thing that it needs to do is you know, cancer is like a terrorist. It's on or like a criminal. It's on the run from the immune system. So it's constantly got to throw those. You know, what do those planes do? They throw those spark things off the back, right? I need to know what the name of that is. The decoys, right? They're constantly throwing decoys and things to fool the immune system. The other thing that the cancer cells do is they send these messages. They're chemicals or the nanoparticles that carry code to co-opt other cells to help them. So, for example, to grow, cancer needs food and oxygen. So it needs the surrounding tissue to grow vasculature, blood cells. It can't do it itself. So it sends these messages out. Hey, listen, I'm a good guy. You know, we really need, I kind of look like a wound, and so you've got to come in here and grow more blood vessels. And so it will then grow because of the blood vessel. So it's constantly sending those messages. Then when the immune system interrogate, oh, what are all these blood vessels here? What's going on here? Nothing to see here. Everything's great. It's all the usual suspects. Everything's fine. So this is a very complex dynamic. It's a very complex dance. It's like a city. And it's those messaging systems that are important for the survival and growth of the cancer. That's what we hack into.
Oh, that's really good.
yeah.
Does that help answer?
Yeah, it does, because I was just wondering why cancer cells wouldn't need to send messages, and why that is important that the immune system interacts with those messages, and then you create new messages to tell the cancer cells. I mean, what's the immune system send back to the cancer cells to fool them?
So the immune system, you've got multiple aspects of the immune system. The cells themselves have their own system of checking if there's any problems, and then they'll die if there's a problem, because they you know, We don't want an out-of-control cancer. The other bit is the cancer cells are constantly on the run from their multiple aspects of the immune system that are trying to remove any erroneous cell. So there's multiple methods that the cancers use to avoid the immune system, and if they blow it, they get killed by the immune system. In fact, the immune system, we believe, clears most cancers, but sometimes there'll be cancers that pull a trick out of the bag to avoid the immune system, and sometimes they'll fool the immune system to help them. That's all messaging. It's chemical messaging, it's molecules that the cancer is emitting, it's nanoparticles with code that the cancer is emitting. That is what we hack into.
Wow.
That's clear.
It's pretty clever. It's a mad guy.
I don't know about that. The students are clever. I'm just an occasional show pony, right? That's
Come on, you're not just a show pony, are you?
But that,
you asked, what can I reflect on it a little bit? I maybe brainstorm with you. I'd love to encourage more.
Sorry, can I just get you to move to your-
Yeah, sorry about that. I'd love to encourage more students to get involved in STEM, young people. There's so many opportunities here. And there are so many opportunities, particularly for students that train in the mathematics, chemistry, physics. We don't have enough for a lot of the job opportunities that are emerging here in industry, academia, and in government. And the other bit is to encourage young people to get involved in this space. It's such an exciting area right now, and I can't think of a better adventure.
Why aren't they? I mean, who knows?
Whew. Boy, now we're getting into social dynamics.
I was just going to say, when I was a kid, like a primary school, up to that, me and all my mates, what do you want to do when you grow up? I want to be a scientist. But it's not sexy anymore. Now you've got
Yeah.
people questioning science.
Yeah.
Is this part of the problem?
Better look at me when you answer.
I thought we were just going to talk about cancer and so. Why aren't they?
Parcels.
It's an interesting one. I think part of it that I see with our community is this. It's become harder to buy a house, to live in a place like Australia, and so there's such a focus on money. I've got to, my parents want me to get a good job, and that's this type of area, that type of area. I need to get that because I can get the house, then I can get to this, and and I think that creates a bit of a railroad without that obliterates people's passion. And so I've certainly seen career decisions for young folks. In fact, if you look at subject selections for our university, you'll see some of the brightest students will elect, and I don't want to pick any disciplines, but they'll simultaneously elect law, business, and medicine. Now, are you telling me that they're actually passionate about all three, or that perhaps they're making a financial decision pressured by family or pressured by their social network or whatever? I certainly see that a lot with students. And actually, we also pick up a lot of students, and I'm really delighted by this, who have gone into those areas and just realised, in fact, I admire their courage. They realise, you know what, it's not for me. I'm going to go back and do science. There are careers in science. They are reasonably well paid. I think they're better paid than many other careers that I've seen. And it's such an exciting area to get involved in. It's an area where industry is growing, particularly in this country. And I can't think of a better place to spend your life or spend your career.
Perfectly put you by science is suitable for everything.
Yeah.
And we agree
What's
with
that?
everything you say. It's
Yeah,
good.
that's it.
Everything you want to say.
Anything I want to say? Oh my goodness. Look, I just feel I feel so grateful to the people around me. I mean, I come to work every day. I feel so lucky to. I mean, I'm not flipping burgers. I'm not that immigrant kid, refugee kid anymore. Maybe I will be in the future, but I'm surrounded by just the most fantastic people in our lab. I feel so humbled and grateful to them that we're able to spend our time together working on these really big and really important problems, and that we can do that here in Australia.
Well said.
That was perfect.
I know you're just cynic, you still believe Hippocrates had nothing to do with medicine.
Okay.
And you've
Speed
and rolling and one second
and slow.
okay, and when you're ready.
So this is the single molecule readout chip. It's a tiny little opalescent dot on the silicon wafer, which contains millions of these little nanopillars. And so what we do on the chip is we take a drop of blood and catch on every single pillar one nanoparticle that is like an email, a single email that the cancer cells are sending to the immune system or to each other to communicate important information. It's by catching these and reading them on the chip, we're able to hack into that process that the cancer is using. It's critical for its survival, and if we can get that information, that helps treat the cancer. Here you can see what we've done for lung cancer is by reading these information from a drop of blood, we can differentiate a patient or patients that have malignant or benign lung cancer. It's a really difficult problem in the clinic that requires either complicated imaging like a CAT scan or a PET scan, but with this chip from a drop of blood, we can get the same information, often better information. It's really important for the trajectory of a cancer patient to help them survive.
Line lines.
No, good.
Just lines.
Yeah, where you are is good.
Okay.
Okay, we'll just try that
A
again.
bit jarbled, or is it okay?
No,
What-
I'm just going to go again. I'm going to do different lens sizes and I'm going to zoom around and do it. I'm
Okay.
gonna play silly buggers with the camera while you do it again. That was great.
Was that right?
Same.
It makes
Okay.
sense.
You follow the-
How
follow
new
the
is this?
basketball.
Has it been adopted by anyone yet? Or?
No, we've only just developed. So what we do here is we perform the research here. We publish our findings, and then we look to translate the technology into the hospitals and through
I
commercialization.
was not on the screen. Not on-
Okay, we had you
totally
cut.
useless. I know, but it was totally useless. And then start again. So, thank you.
I love it when you guys are doing your little thing. It's
We've known each other a terribly
it's
long
like a
time.
little lovers tiff. It's so good.
Rolling.
So this is the single molecule readout chip that we use to get information about an individual's cancer to help with precision medicine. Here, what we're doing is you can see on the surface of the chip, we have millions of these little nanopillars. So a drop of blood is placed onto the chip, and the chip interrogates just one nanoparticle. These are called extracellular vesicles. They're emails that cancer cells are sending to the immune system to avoid getting killed, or emails that they're sending to surrounding tissue or other cancer cells. This information is critical to determine whether the disease is benign or malignant, or to help in choosing the medication that's used to treat the patients. For example, whether immunotherapy could be useful to save someone's life, and whether immunotherapy might be dangerous for that person because it could cause toxic effects.
And once more, that was great.
Was that all right?
Yeah.
That's good.
Okay, and when you're ready.
So this is the single molecule readout chip. It's the little opalescent dot on the chip. And you can see a magnified picture here. It has, whoops, sorry guys.
Start that again. That's okay.
Yeah.
Yes, it's all up.
Go again.
And when you're ready, and
So this is the single molecule readout chip that I mentioned earlier. It's the opalescent dot on the silicon wafer, which contains millions of these.
sorry, we should do that again.
They're just tight on it. So if they're
Titering.
they're tight on the image, so if they
Ah.
don't quite
I'm
land
also
perfectly-
Ah, yeah,
going back
okay.
and forth like that anyway.
Yeah.
So this is the single molecule readout chip. It's the little opalescent dot in the center of the silicon wafer, which contains millions of these little nanopillars. Each nanopillar can read from a drop of blood. We put a drop of blood on the chip. Each nanopillar reads a single extracellular vesicle. This is a nanoparticle that's like an email message that the cancer cells are sending to other cancer cells, sending to the immune system or the surrounding tissue. By reading these nanoparticles one at a time, we can get really important clinical information about whether the cancer is malignant or benign. We can get more accurate information often than imaging, but we can also tell whether the patient will be a good responder to medications like immunotherapy that could save their life, or whether they're a bad responder to immunotherapy that could damage some of their other tissues while they're being treated. So it's a key technology that we see to enable this area of precision medicine.
And we'll try once more. I'm going to try a different effect now.
What's that, sorry?
We'll go once again. I'm just doing different shots.
Okay, sure.
That's great.
Same thing, same
thing.
bab,
Yeah.
same
Hey,
bab.
Do you know what you're talking about yet?
Not really.
Great.
It's, so this is a single molecule readout chip, and you can see the little opalescent dot on the silicon wafer. The opalescent dot has millions of these little nanopillars that are used to detect single nanoparticles emitted by cancer cells that are sending messages to the immune system and the surrounding tissue. By reading each one individually, it's a completely new way of monitoring cancer, of monitoring the circuitry of cancer, so that we can firstly determine whether the cancer is malignant or benign with greater accuracy than imaging technologies like X-ray, CAT, PET scans. But then also we want to optimize the treatment for the patients with lung cancer so that we can determine whether they are going to be good responders for example, immunotherapy, which could save their lives, or if the immunotherapy might actually harm them, in which case a different type of medication needs to be used. So we're very excited about using this sort of technology to guide this area of precision medicine.
Genius.
I don't know, I hope it's not too garbled. Is it okay?
Keep rolling,
No,
don't
you're doing
cut.
great.
So this is new. How
This is brand new.
This? Just, okay.
Very new. We developed this only a few years ago. We engaged in a clinical trial, and we've published our results in late 2023. So it's literally just 1 year old.
So what's it going to do from here?
So we're developing a range of these sort of technologies, and the pathway that we use is we do the hard stuff, which is, attack the hard problems, find new solutions, create new technologies. And the university has a system of patenting those ideas, patenting those inventions, and then it partners with larger companies to commercialize and convert those technologies into products that could be used by hospitals and pathology labs. So
Anybody else in the world been doing something like this, or is it unique to you guys?
this particular technology is 100% unique to us. It was invented here at the University of Queensland. We were the first to publish it. We've got a series of publications in this space. We're very proud of it.
What's been the reaction?
Well, the reaction's been pretty good, to be honest with you. We've had, we're really grateful for that. Strong support from the scientific community, strong support from the clinical community, and a real push to develop these further, to see how far we can go. So we're constantly improving this technology to get more information. We're developing another technology to, rather than just reading the information, we then on the same chip synthesize exactly that message to send back into the body and hack into the system as a novel therapy. So we've been lucky enough to receive some new grants in this space to develop it further. We're also having conversations with industry partners about how to translate some of the already made discoveries out into the clinic.
Pretty impressive.
Thank you. It's a real honor to work on this with the team that we have.
I'd be feeling kind of good about it, huh? Or you?
I feel lucky to work in this space. It's better than flipping burgers.
Was clap, hand clap at the end of
Second clap, please.
second hand clap at the end of very naughty.